So what I want to look at today is the concept of the inverse trig function. Okay? As we think about inverse functions, inverse trig functions, I want to take a step back in our minds and think about the inverse trig functions, or the inverse functions that we dealt with in the past. Okay? First of all, just thinking about what an inverse function is in general, and then also, when did we have an inverse function? Okay? So can someone tell me, what is an inverse function?
The reciprocal?
Well, the reciprocal is an example of an inverse. Okay, you could switch the y and the x. Alright?
1 over the function equals the inverse function.
1 over, that's an example of an inverse function. But it's not necessarily always just going to be 1 over. Yes?
Is it the reflection through y equal to x?
That's correct. It is the reflection across y equals x. So we have two things there. We switch the x and the y, but also it's a reflection across the line y equals x. So let's use the example of sine here. Instead of y equals sine of x, we could switch it and make it x equals the sine of y. Now, we would have to solve this, okay? And in order to solve it, we have to use what's called the inverse sine function. Okay? So we take the inverse sine of the sine of y. And if you remember, back when we talked about inverse functions, we had f inverse of f of x, and that always equaled x. Alright? We also could have taken f of f inverse of x, and that would have given us x. That was the definition of what an inverse function was. Okay? That notation is the notation we're using here. Do not confuse that for the exponent -1. This is not the same thing as cosecant. Alright? We're not dealing with cosecant here. Okay, this is an actual inverse function, and anytime I teach this, there's always some that are thinking of that in terms of cosecant. It's not an exponent, it's actually notation to indicate the inverse. Okay? Now, using this same concept here, right here, what would the inverse sine of y equal?
Y.
It equals y. And y would then equal the inverse sine of x.
Because the inverse sine is just equals the x and y switch.
Because we switched the x and y and then solved it. Now, what the inverse sine does is this, okay? If you remember when we were talking about a function and its inverse, the function would take a value, okay, from the domain, here's our domain, and map it to a value in the range, okay? So for example, you guys know from the unit circle that if I have 45 degrees, let's say the tangent of 45 degrees equaled what? Do you guys remember?
32 over 2.
So it's 1, yeah. Okay? Now watch this. The inverse function, the domain is going to be the range of the original function. And its range is going to be the domain of the original function. So
10 -1.
if I had the inverse tangent of 1, that would map 1 back to 45 degrees. Okay? That's what these inverse trig functions do. Okay? They take an angle, they take a value and they map you back to the angle that has that trig function. Okay? Alright? So again, tangent takes 45 from its domain and maps it to 1 in its range. The inverse function, inverse tangent, takes the 1 from its domain and maps it to the 45 degrees in its range. Okay? So the domain and range simply switch. Okay. Now, we've gone through all that, but we have a bit of a problem. We have a problem because if I used sine and I actually did reflect it across the line y equals x, check out what I'd have. I'd have that. Now, can someone tell me what my problem would be?
Wait, what is that again?
This is not.
That would be if I took the sine curve and I reflected it across the line y equals x. It would look something like that.
This is not.
Reflect to y?
Oh,
Or
is it
is it
the
compressed?
outside of the domain or something?
No?
Compressed?
No?
When you draw this out, like if you made a table of values, would you just switch the x's and the y's?
Mm-hmm.
Outside of the range?
It wouldn't
No?
pass the horizontal y test.
Wait, what?
It wouldn't pass the horizontal line test.
Okay. It wouldn't, this would not pass the vertical line
That's what I
test,
mean.
right?
Not really.
If I were to draw a vertical line, okay, that is certainly not a function. Okay? That's not a function. So that's the problem. Now, we faced this problem once or twice in a couple of the problems we worked at a while ago. How did we force it, a function, to be able to have an inverse function?
You restrict the domain.
Yeah, that's exactly right. We can restrict the domain so that the part we are looking at will have an inverse function. Okay? Now, can anyone tell how we could tell just by looking at the original function that it was going to fail the vertical line test? What?
Just draw a vertical line.
Well, if I draw a vertical line, I know, like for example here, sine is a
Well,
function.
it has multiple zeros. So it's gonna always, if you rotate it, it's gonna always have more than one value for every zero.
That's true. That's true. Does anyone remember how we could tell just by looking at it?
Just have, was that here?
Yeah.
Dang it.
It actually was mentioned already accidentally.
Horizontal line.
Yes, the horizontal line test. Okay? Here's the deal. If I cross this through a function, a horizontal line, and I hit that more than once, then when I reflect it across the line y equals x, a vertical line will hit it more than once. Okay? So we have the horizontal line test. And since this is failing it, I know it's not going to have an inverse function. Okay? So, like Samantha said, we want to restrict the domain. Okay? We want to restrict the domain so that we get a part of it that is one-to-one. That was the term we had for functions that had inverses. They were one-to-one. They passed the horizontal line test. Okay? So, what I want to do here, let's think about sine and see if we can come up with a way to limit just sine so that it would be one-to-one. Any thoughts?
You get the absolute value.
You can cut it.
Make absolute value? No, we can't do that. We gotta just
Right.
that, huh?
Amplitude.
Well, the amplitude is 1.
And you just, never mind.
Period.
If you like, didn't let it get bigger.
Yeah, change the period.
That's
Well, we don't want to change the function. We just want to limit the domain.
Horizontal
Just
translation.
with the period.
Limit the domain.
I'm only going to let x be certain values. Okay? Let's say I tried 1 period of it. Okay? If I just included from 0 to 2 pi, would that pass the horizontal line test? No.
It has to be 1.
No. Okay? Because as soon as I reach here and start to come down, I failed. Alright?
It'll only be like 1/4 of it.
Okay. So let's look at that. If I just included 1/4 from 0 to pi over 2, okay, is that 1 to 1?
yes.
Yeah.
Yes. Does that account for all the possible values of the sign, though?
No.
No.
No. So I would have some gaps here, right? What part of the sign values am I missing? I have from 0 up to 1.
What if you go back to negative pi over negative pi half?
So like back to here?
Yeah.
Does this include all the possible values of sine?
No.
Yeah.
Yeah.
Yeah, it goes from -1 all the way to +1,
It's
right?
the same on the other
Yeah.
side.
Okay, and the other side is kind of a reflection of it, alright? That's actually what we're gonna do, okay? That's what we're gonna do. And the fact of the matter is, you might say, well, what about these angles over here?
The same thing.
Just
We can get these angles because they have the same values of the trig functions. What would they have in common? If the value of the trig function is the same, those two angles have the same.
Distance between one and the other.
no, the y-axis, the same sign.
Range.
No, we saw this on the unit circle, the same reference angle.
Oh.
Okay. We're gonna use, we only have half the period here, right? This is only pi worth of angles, from -pi over 2 to pi over 2. But we will use reference angles to be able to get the other half. Okay, we'll see that later on today. Okay? So let's take a look at sine. Okay? We just said that we are going to limit the domain from -pi over 2 to pi over 2. So instead of having all real numbers, we're going to limit it,
Flip it
and now we can flip it like we have over here, and notice that will pass the vertical line test.
Yeah.
So that is a function, okay? Notice too, what we learned about inverse functions before is still true. The domain of a function is the range of its inverse, and the range of the function is the domain of the inverse, okay? Now, the same thing or similar thing is true with cosine. How could we limit the domain with cosine to make sure it's 1 to 1?
0 to pi.
0 to pi, okay? If I go 0 to pi, I get this portion of the cosine curve that passes the horizontal line test, okay, and accounts for all of the different values of cosine. Okay? So instead of all real numbers, I'm going to make it 0 to pi. And now notice over here I have the arc cosine, the inverse cosine. The domain of cosine is now the range of my inverse cosine, and the range of cosine is the domain of my inverse cosine. Okay? And like we mentioned earlier, remember arc cosine would be the same as the inverse cosine. Okay? Same thing. We use them interchangeably. Okay, does that make sense?
Yes.
Alright? Now, we also have tangent. Okay? Tangent, this one's kind of nice and easy because the asymptotes kind of help us out here. We're going to limit our domain for tangent to go from negative pi over 2 to pi over 2. Notice I'm using parentheses here for my interval because I still do have asymptotes there, so it can't equal a negative pi over 2 or positive pi over 2. Okay? But I'm looking at just this portion of tangent. Okay. Now, the vertical asymptotes I have here are now horizontal asymptotes. Okay. Notice the domain is now the range, and the range is now the domain.
So it's reflected across the x and the y?
It's reflected across the line y equals x. Okay? Alright. So, not too bad. Okay, so what I want to do at this point is we need to learn how and when to use these things. Okay? So if you look at our next slide here, I want you all to get out your calculators. And not your iPad calculators, the calculators that you will actually use when you're taking your tests and such. Alright? So that you will learn how to use this. Okay, so just to make sure that we're all on the same page here, let's make sure we know how to solve this. We have sine of x equals 0.5, and you probably already know from your unit circle what the answer should be. But just so we could get practice using our calculators, we would say that x, in this case, would be the inverse sine. So you're going to hit second sine on the calculator. Inverse sine of 0.5. And what does your calculator give you? 30. 30 degrees. Okay? So, what I want you to do, either by yourself or with your neighbor here, I want you to go through the rest of these, and I want you to figure out what the angle is. One thing though, listen please. If you get a negative, I want you to convert that to a positive coterminal angle. How would we do that?
Inverse 360 minus the angle.
Yeah. 360 minus the angle, or just add 360 to the negative angle. Okay? So convert those negative ones to positive ones. Alright, so if the cosine of x is 0.7, what does x equal? 45.56. Alright, so let's do that 45.6. We'll go one decimal place. Okay? If tangent is negative 8, x is how much? 277.1. Okay. How about if sine of x is a negative 0.8, what do you get? 306.9. So for that one, guys, the calculator gave you what?
Negative value.
A negative, what was it, 53.1?
Yeah.
Use
Yeah.
300.
Okay. And on the previous one, what did the calculator give you? I know it did give you 277.1.
Wait, what did, oh.
It gave you a negative...
Wait, I got it. Negative 82.87.
Are you okay?
0.9.
Okay. So you got that. On number 5, the cosine is negative 0.2, so what is x?
101.5.
101.5?
Yep.
Okay. And if tangent is a negative 2.3,
293.5.
Originally negative 66.5.
Nice.
okay. So as you guys can see already, if we're doing equations that represent real life situations, okay, any type of thing that we're trying to calculate to be able to use, already you're going to have to keep in mind and think about the answers that your calculator is giving you, right? If it gives you a negative, that's not particularly useful if we're trying to like build a bridge or something, okay? However, when we find the positive coterminal angle by adding 360 to it, then we have an angle that we can actually use, alright? Now, here's the thing though, okay? You guys were working on it, you got those. Here's what I got. Okay? This one's hard to see. 113.
Oh, you did 180. Oh man. What? If it's acute, you did 360. If you, I don't even know anymore. Because no, 30 plus 150 equals 180. 45.6 times plus 314.4 equals 360. Same goes for 92.1. Same goes. Oh, that's gonna equal 560.
Oh, are you in different quadrants?
You're doing something.
Wait,
You're
what?
Are you in
adding,
different quadrants?
I am in different quadrants than you guys.
You're adding a whole.
You're doing
you-
180.
Yeah, you're
180
adding.
minus.
You're adding quadrants.
180 minus 30.
Wait, whatever it's closer to, whatever
horizontal,
horizontal
yeah.
thing is closer to.
Okay, so what are we using there?
Reference angle.
The reference angle.
Yeah.
Why would I use a reference angle and get something in a different quadrant?
If
Because they have the
it's
same.
negative?
No, it's because like they all have the same value, just like different angles.
Okay, they have the same value but different signs and they're different angles, right? So they meaning the different angles
Oh, you mentioned the
that have the same
Values.
reference angle, right?
Exactly.
If we have the same reference angle, you're going to have either the same value for the trig function or possibly the opposite. So the only thing that'll be different is the plus or minus. Remember, we saw this on the unit circle. For example, on the first one here, 30 degrees had the point root 3 over 2, 1/2. But 150 had negative root 3 over 2, 1/2. That was at 150. But the reference angle was still 30. And then down here at 210, we had negative root 3 over 2, negative 1/2. And at 330, we had positive root 3 over 2, negative 1/2. Okay? But the thing is here, why did I just do the 150 and not the 210 or the 330?
Negative.
Because those ones
All
were
students
negative.
take calculus.
There we go.
Very good.
The thing that we've got to keep in mind is this right here. Okay? Remember when we limited our domain? For sine, we limited it to be like this. And we said, wait, that's only half the period. What about the downslope on the other side of the period? Well, we're going to get those answers by using our reference angles. Okay? So here's the thing. We've got to remember our arc cosine or arc sine or arc tangent is only going to give us a result within that area that we limited the domain to. Okay? So, how do we find answers that are outside the range? Remember we had sine going from pi over 2 down to negative pi over 2. Cosine, we limited it so it just went from 0 to pi. And then tangent, we limited from negative pi over 2 to pi over 2. Just so you can see it a little bit better. Okay? So how do we find the answers that are outside that range, that we know exist, but they're outside the range for our arc cosine? Well, or arc sine, or arc tangent. Well, first of all, we need to consider, and you can do this part before you even use your calculator, consider all students take calculus to find which quadrants your answers are going to be in. If you have sine of x equal to a negative number, you know you should get an answer in the third quadrant and the fourth quadrant. Okay?
Yeah.
Then use the calculator or the unit circle to get one of your answers, and then use the reference angle to get your other answer. Okay?
Yeah.
And that's all there is to it.
Didn't go across.